Hi guys, welcome to the next lesson. If you want to pause here and attempt to do now questions, I'll put the answers on in 2 seconds. And here are the answers to 2 now questions. As ever, we'll talk about this on Zoom if you want to have a discussion, but hopefully these are the answers or similar to the answers that you put yourself. So this is lesson 1 of week 3. We're going to talk about Georg Ohms, and we're going to specifically talk about Ohm's Law. Ohm's Law is related to electricity and more specifically electrical circuits. So we use electricity all the time, but we might not understand how it actually works and what it looks like in a circuit. So I'm going to explain a little bit of the background first, then I'm going to explain explicitly what Ohm's Law is related to. So we know electricity is one of the 4 fundamental forces. We spoke about it at length last year as being one of the fundamental forces, and we can see raw electricity in the form of lightning. So what is lightning? Well, essentially lightning is related to centres of positive charge and centres of negative charge, and the electrons are trying to find an equilibrium. They're trying to get from one end to the other. So when you have a mix of positive and negative charges, then you can create some disparity. So you can see these clouds here have positive charge in the top, negative charge in the middle, positive charge near the bottom, and depending what charge is on the ground, then lightning can actually go all the way through that towards the ground and create a sort of circuit. So it's to do with positive and negative charges, and the movement, the electricity that we see in lightning is the movement of electrons. So we know that electrical charge distribution in a thunderstorm, when the electrical charges become sufficiently separated in a thundercloud, with some regions acquiring a negative charge and others a positive, a discharge of lightning becomes likely. Cloud to ground lightning is initiated by a preliminary breakdown process within the cloud, typically between the centre region of negative charge and a small positive charge below it. So we saw that there in the previous picture. You have different charges within the cloud itself, which is then going to cause lightning strikes. So looking at electricity in a more controlled version, I guess, is the electricity we use. So I'm using a lot of electricity right now. I've got a lamp on beside me that's plugged into the wall. I've got my Macintosh laptop, which is on charge. I've got a microphone charged in. I've got my headphones in. You guys are hopefully watching this on a screen where you have to be, that is using electricity, the internet and everything else. So our daily lives are consistently, everything that we use in modern life uses electricity in some degree. Without electricity, we wouldn't be able to use our phones, and our communication system would be much more limited than it is. So it's important to understand how electricity works. How does the electrical circuits in your house work, and why can we use it in all of these different applications? And one of the ways that we can understand how a circuit works is using Ohm's Law. So I'm going to explain that in a little second. First, let's just very briefly remind ourselves the structure of an atom. That's important. The protons and neutrons make up the nucleus of the atom. We have neutrons with no charge, protons with a positive charge, and electrons in the electron shells. For those of you who remember, 1 proton was hydrogen, 2 protons is helium. So this one has 3 protons, it must be lithium. And lithium is really important. You may have heard of lithium batteries before. We use that as the chemical in batteries for a whole bunch of reasons. Essentially, when we're talking about energy, or the flow of electricity, I should say, we're talking mainly about the electrons, perhaps unsurprisingly. So the electrons, as they move from one atom to the next atom, that is basically the flow of electricity. It's quite hard for us to imagine that. There's no real world sort of examples. We can't see the electrons doing that. So one of the good analogies we can use is like water. If you think of water moving around some pipes, say we have the water pump here, pushing, it's causing pressure, it's causing the water to flow through the pipes. Imagine that if we restricted that pipe and made it thinner, then that is going to reduce the flow rate going through the circuit until it gets back to the pump and it's pushed through again at a certain pressure. So that makes sense for water, okay? We're going to have high areas of pressure of water coming through. When they get squeezed through this smaller part of the tube, it's going to slow everything down and you're going to have a lower pressure on this side, and the pump is going to be pushing the water around. So we can use the same analogy when we talk about a simple circuit. When we look at a battery has a plus and negative on one side. On the positive side, it's sending out the electrons, okay? It's pushing it out like the water pump, depending on how many volts are in that battery. We'll talk about that in a little second. The flow of electrons then goes through the circuit here, through wires instead of pipes. We can also limit the flow of the electrons by putting things called resistors, okay? And they're usually drawn, these squiggly lines here, to show that the flow of electrons is getting squeezed, and then the flow is going to be lower here than it was on this side. And the flow rate, when we talk about electrons flowing through, this is called the current, okay? The current is measured in amps, and it is depicted here by the letter I. Don't worry too much about that in a moment. Resistance then is measured in ohms, which is named after Georg Ohms, unsurprisingly. And then the power supply is measured in volts. So we have three variables there. We have voltage, current, and resistance. And these are the integral components, the trio of numbers that we need to be able to calculate Ohm's law. So we're talking about electrons flowing through the circuit. This is something, another way that we can kind of imagine it. If you look at a circuit, you have your battery, the movement of electrons, all electricity is electrons flowing in a certain direction. So the electrons are flowing from this battery through a circuit to provide energy for this light, and then they go back into the battery and the circuit is complete, okay? So all we're talking about when we're talking about current is the flow of electrons through a circuit. So I mentioned this guy's name a couple of times, Georg Simon Ohm. He was a German physicist who discovered the law, named after him, which states that, so pay attention to this, the current flow through a conductor is directly proportional to the potential difference, the voltage, and inversely proportional to the resistance. Let's try and say that in simple terms. So the flow of electrons through a circuit is related to the power potential, the voltage. That makes sense. If you have a bigger battery, as in you have more volts in your battery, therefore you're going to have more current or more electrons flowing through that circuit. Okay, there's more power. So imagine if we look at think about our water analogy again. If you have a bigger pump, pumping water through the circuit, then the flow can be higher. You can increase the flow rate of water if you have a bigger water pump. The same goes with electricity. If you have a bigger battery in terms of voltage, then you can increase the flow. So it's directly proportional. That part here, directly proportional. That makes sense. Bigger battery, higher flow rate. And this is inversely proportional to the resistance. That makes sense too. If I put more resistance onto my circuit, I'm going to decrease the flow rate. The more that I resist my circuit, so the more resistance I have. So for example, we're using the water analogy again. If we make the pipe really, really small, you're really going to affect the flow rate. The same thing can be said in electricity. If we use a resistor to slow the flow rate, depending how big that resistor is going to depend how much the flow rate is stopped or slowed down. So that makes sense, okay? Intuitively, that makes sense. But we're going to do lots of really simple examples to prove this. So I'm going to break down, I've talked about voltage, current, and resistance. Let's really see what I'm talking about here. So the voltage is what makes the electrons move through the circuit. It's the push, essentially, that causes the charges to move in a wire or another electrical conductor. So the way that I like to imagine it is, imagine you have a tap and you turn the tap just slightly, the water is going to come out and it's not going to be much of a high flow. If I open that tap a lot, i.e. I put a lot of pressure through there, it's going to push a lot of water through. So you imagine your 9 volt battery here, okay, it's going to be able to push a certain amount of electrons through the circuit. If that was a 90 volt battery, it's going to push even more through. There's more pressure it can put onto the circuit. Current then is like the water flowing through the hose. An electric current is a flow of electrical charge around the circuit. So you can have a high flow or a low flow, and how you design that circuit, so the flow is really affected by the pressure of the tap. We talked about voltage, but also the diameter of the hose or the resistance. So the flow rate is really linked to the power supply and the resistance of the circuit. And the resistance then is an electrical quantity that measures how the device or material reduces the electric current flow through it. So you can have less resistance or more resistance depending on what kind of resistor you have. And resistors are just tiny little things that you can put into a circuit that basically condense the flow rate. Okay, just like if you squeezed on a hose, you're resisting the amount of pressure in that hose, then the circuit, the current is going to be reduced. Why would you want to do that in an electrical circuit? Well, for example, I'm plugged in just now to my laptop. And imagine my laptop has got some quite delicate electronical components that if you gave it a massive surge of electricity, then it would actually damage the electrical gear. Just because you have a lot of energy available doesn't mean you want to use all of it at the same time, particularly when we're using or talking about sensitive electrical equipment. So it makes sense to put a resistor on circuits to really allow us to control the flow of electrons. How much energy do we want to be flowing in that circuit? We want to be in charge of that. We don't want to just say, okay, there's 12 volts and if I plug something in, it's going to get all 12 volts. If I don't want it to get 12 volts, I should be able to adjust that appropriately, and we can. So the analogy I've been using is like water. So voltage is the pressure, current is the flow rate going through the hose, and resistance is like the thing slowing down the energy. How do we measure these things? Well, luckily we measure voltage using volts, and that's just simply a V. Current we measure in amperes or amps, and this is usually written as an A or an I, and don't ask me why for I at the moment. And then resistance is measured at ohms, which is sometimes written as an R, or we use this funny little symbol which is the omega symbol, and I'll explain in the next lesson why we use that symbol. So how did Georg Ohm, I should say, come up with this idea? Well, he was German and he knew an Italian called Alessandro Volta. No points to work out what he invented. And he invented a battery, and he asked, can I use your battery? And Volta said, yeah, that's fine. And using the battery and creating really simple circuits, Georg Ohm discovered this relationship between voltage, current, and resistance. And we're going to be looking at that in the next lesson. So we have a really simple circuit here. And just to explain what's going on in the circuit, you saw it before, but this is how we write a battery, essentially. Instead of drawing a big battery, we do a short line followed by a long line. And this is our battery, so this is where the voltage is. The circuit is then connected by wires. Then we have our resistor, which is stemming the flow of the current. And the current is all the way through these black lines here, okay? So we have volts, current, and resistance. So this is essentially Ohm's Law. So Ohm's Law is a mathematical equation. And if you can remember this triangle, V over IR. So the way we write it is this triangle here. We have V over IR. This can be written in multiple ways. So V, remember, is voltage. I is current. And R is resistance. So how do we look at this triangle? So we have the V on the top over the I and the R. What that means is V is equal to I times R. So the fact that I and R are on the base of the triangle means that they're being times together. If I wanted to calculate I equals V over R. So current equals volts over resistance. And if I wanted to calculate R equals V over I. R equals voltage over current. So when you first see this, I agree, it doesn't look good at all. It looks horrendous. But it's very, very simple algebra. And we're going to do some really simple examples in the next lesson. All I need you to try and remember is if you can draw this triangle out from memory, and then realize that, okay, if V is at the top, I bottom left, R bottom right, then V is going to equal I times R. If I want to work out the current, which is I equals V over R, okay? And if I want to work out the resistance, then R equals V over I. And the way that this triangle is written allows us to make those equations. I'll explain that in the next video as well. But just to remember, volts is the V, current is amperes, which is an I, and resistance is ohms, which is an omega, or just R. I'll explain these a little bit better in the next lesson. Okay, thank you very much. That is Ohm's Law in a nutshell. Hamish is telling us that the average American spends about 2.5 days a year looking for lost items. I think in my case, you could probably make that a week. I'm always losing things. I don't know what it is. But yep, thank you guys. I'll see you in the next lesson.